Oh, okay. Well, my name is Bill O'Keefe. I'm going to talk a little bit about how to protect your data in sensitive environments nowadays. I started out in medicine many years ago, about 45 years ago, and quickly found that as in medicine, which is highly specialized, you have to pick a subspecialty and make the most of it. And I specialized in cardiovascular, ultrasound, and venous disease. In one of our first labs, we decided we needed to, this was back in the 80s, needed to have some way of monitoring our patients. And so we found a little brown box called a Macintosh and started playing with that. And it had a basic disk in it. And that was the beginning of my programming. And over the years, we extended that until we built it into a fairly large program that we had installed in quite a few hospitals in South Texas, clinics and the such. And it was an incredibly horrific program, code-wise, not having any basic background myself. But we did manage to produce over 1 million reports in the 10 years that it ran. And then this was back in the non-HIPAA days, so we had patient information flying around through cyberspace, and regulations and technology overran us, and we let it slowly die out, and I said never again. And then about 5 years ago, I retired, had time on my hands, and switched to Xojo, and here I am again. So I'm looking now at doing DICOM management in medical imaging, and the DICOM file is a very interesting file, what I was going to talk about today, but then I realized halfway through that I shouldn't be talking about medicine here, but talking about something else. And in working on encrypting the file, I got interested in all the different types of encryption. And that turned out to be like medicine. It's as deep and wide as medicine is, and you have to kind of pick a place to specialize in. And so most of my medical stuff fell in a regulated environment for encryption. And if you want to have a program that runs in one of these types of environments, government, large corporations, or medicine, you need to adhere to a certain set of rules in order to even be accepted or they'll even listen to you. So what we did was start looking at how we encrypted things and all of the different ways of doing it, and we found that there's a number of organizations that control this. It's kind of an acronym hell. It starts with NIST, which is the National Institute for Science and Technology, or Standards and Technology, and they produce a document called FIPS, the Federal Information Processing Standard, which describes which of these algorithms you're going to use. NIST says these are the ones you can use, and FIPS says these are the ones you're going to have to use. Plus, you're going to have to be validated. So if you want to actually enter these fields, these environments, you have to have your encryption modules validated by the FIPS organizations, or an organization that is certified by them to test you. And that takes months and many tens of thousands of dollars to get to. But it's a long, arduous thing. Fortunately, it boils down to just a few algorithms that you need to deal with. But this is one of the early problems. And it's amazing how apropos this can be. Early on, I had people scotch taping their passwords to the monitor, and one in San Francisco Bay Area, she would tape it to the top of her keyboard, but turn it upside down, and that was her encryption. Yeah, now that didn't work too well. So the weak link in all of this is the password, the person holding the password. And everything else is pretty resilient. The technology is there, the algorithms are there. Nobody's going to rewrite the algorithms. They're already done and spoken for. And hopefully such things as biometrics will help improve this in the future. But for now, the password itself is the problem. So how do we protect the password? And that's what we're going to talk about today. Encryption can be very tight as long as you handle the password properly. And the password should never actually touch the disk. It should be the secret and should never come out anywhere. So the DICOM file that I'm dealing with is a massive file that has quite a few different parts to it. And if you can encrypt the file, if you can analyze it and encrypt the file, then you're pretty much on your way. So the problem is getting away from that password, producing another key that has nothing to do with the password itself. And these hackers are everywhere, and they're very, very good at breaking encryption. So the common mistakes are here. The most common one probably is keys being stored alongside the data to protect. That's the person. Using your IVs, reusing them. What happens when you reuse keys in your algorithms is you introduce patterns into the code. And this is what the hackers will pick up on, and they use that to break it. They're not really breaking the cipher itself, but they're trying to break the password. And of course, rolling your own algorithm, you really shouldn't be going there at all. And using the correct algorithm is the next one. Now, it's fairly easy in this environment because the FIPS standard recommends or actually requires that you use the AES 256 GCM algorithm. And that includes with password-derived key algorithms too. The other problem is using strings instead of memory or memory blocks in your data that can introduce encoding problems. So you stay away from string manipulation in your keys. And not having an audit trail. The other requirement is an audit trail, particularly by HIPAA in medical environments, where every bit of data that's touched by a person has to be logged, what they did, who's doing it, and it has to be authenticatable. So the rules already exist. There's standardized AES 256, the GCM mode, and you need a pathway to a key that is very randomized or unique. Most computers nowadays have hardware built in that these algorithms run on, so they're very, very fast. And they grab the key, the IV, and the key for their derived functions from the OS entropy pool. Now, the FIPS demands not just OpenSSL as it shows here, but a compliant path to the OS. OpenSSL will go first down to the bottom layer to the OS entropy pool and grab data from there to seed the key. So you run your key through PBK DF2 for 600,000, it's recognized now 600,000 iterations, and hashing it. And then it's run into the HKDF, which gives you 3 more keys. And one key is your encryption key, another key is your authentication key, and the third key is for an audit trail. The authentication key is not mandatory. It can be used by whatever you might need in your environment or your client, whatever they might require. The audit, though, is used specifically for your audit log and when you log each time the data is touched. So HIPAA requires it. It also requires audit controls. The European organizations all explicitly state similar measures, and it all pretty much falls back to the FIPS standard. So here's a little bit about it. The NIST defines the standards and the FIPS certifies it. And they also say you have to validate it too, and they're the validating organization. So it comes down to the AES 256 GCM, the PBK DF2, and the HKDF, which gives you your 3 keys. And it all uses the HMAC for the audit logging. So if you implement these correctly, you are now compliant with the FIPS standards for doing this. Doesn't mean you're validated, but it means you can be compliant. And that depends then on your client. Is it a hospital that is demanding they see a validation certificate on your encryption module, or are they just requiring compliance, or do they even care? And most of the time, I would go with this because it's the strongest. So the DICOM file includes protected health information, it includes patient data, it comes off a ultrasound or an imaging machine, and it includes patient information, a whole stack of potential tags, up to 4,700 of them, although you rarely see that many, and then pixel data for the imaging. And that can be either a single image, which is fairly small, up to a whole series of slices of images that can run hundreds of megabytes in size. So there is routing information in here, and there's also patient health information. So encrypting the whole thing right off the bat is wrong because you need to get that routing information. So generally when that comes off the machine, it's split, and the routing information, the patient information is split off and put in, encrypted into a database, while the pixel information is then encrypted and put in an area where then the radiologist or whoever's going to read the film can open it up. It's decrypted, he reads it, encrypted again, and they send off their report. So it's all under rest, it's all encrypted during transport also. So it can be small files or very large ones. You need to be able to do this quickly. In a big hospital setting, you may have hundreds of 500 megabyte or gigabyte size files streaming all day long. So you can't allow yourself to get locked up with memory problems. And so the best way to do it, particularly for the iterations in the PBFK, is to go with a background thread. Inside the file, just in case you like to look in it, it's interesting in that it's written in Little Endian, and yet there are several places within the file that can be switched and can switch to Big Endian. So you have to be able to figure that out when you're analyzing a file and switch how you read your data. Now for encryption, that doesn't matter. It's just going to encrypt it into one big blob, and it will decrypt it the same way. But it's an interesting file, and if you can analyze that and encrypt it, you're a long ways down to making it work. So the AES 256 comes down to your keys, your initialization vectors, the modes you're going to use, and it's a multi-function system. You have a block cipher, the CBC, which is 16-byte blocks, and then you have the GCM, which is streaming, and so it only uses one IV in the beginning. With the block cipher, the CBC, each block that's encrypted is dependent upon the block prior to it for its encryption, and so it chains through the entire file, and so it has an overhead in terms of software and hardware, even though they all use the hardware chips now, the AES NI chips, which make things quite a bit faster. But it's not built for parallel processing, whereas the stream is. So we're going to get rid of the password as soon as we get it from the user, and we need to start working on that in order to hide it from the hackers. And that's the whole idea, really, through all of this, is to protect your data. So the OpenSSL MBS is calling directly into the OS entropy pool for a random key. Let's see, this is really, yeah. Whereas the Xojo's native is fine, it's not purpose-built for regulated environments. So right now I believe Xojo only has the CBC as the standard, and it runs off of Crypto++, which is it's a fine crypto library, but it does not include the GCM, and that's what we go to MBS for. And MBS has the random bytes OpenSSL call, so it can get genuine, random, unique information from the OS. So you toss that in with your key to your PDK DF2, which goes through 600,000 iterations of hashing. And this is from another organization called OWASP. It's Open Worldwide Data Protection or Security. There's so many of them. Data Protection System Project. And so they routinely make recommendations based on current hardware and current software as to how many iterations should be done, what some algorithms that should be used. And when it first started, they suggested 1,000 iterations because of the hardware at the time. Now the hardware is fine. We've got the acceleration chips, and so 600,000 iterations of hashing is what they recommend. So NIST says this is what you'll use. FIPS says you have to have it validated. HIPAA says you have to do it and you have to audit it. And then OWASP says this is how many iterations you should use. It's a recommendation, but most everybody goes by it. So the entropy pool is kind of interesting. I hadn't run into this before, but everybody's computer is collecting this information all the time at the nanosecond level. It's looking at random information that's happening inside your computer, keyboard clicks, interrupts, all types of information that's going on, and it's collecting it and accumulating it and creating a state, a number that could be called a state. And let's see if I can get this down now. And if you look at the virtual file that the OS is running, I think I got it there. Nope, I missed CAT. And there you go. And so this is going on actually faster than this. This is how fast the terminal can present it. But it's recording all this data all the time, everywhere. And each one of these represents a particular state at that moment in time of these random events that are going on inside of your computer. And so when you make a call through OpenSSL for a random bytes, it grabs one of these and uses that then to add to your key for a truly random hashing. There's other levels of entropy that they can pull on if the OS isn't available, but nowadays with the modern computers, most all of them are, that's not a problem. It's available. So the first one we use with the password, we send it off with a salt, which is a 32-byte random key pulled from the OS entropy pool. And it's what's sent to the PBKDF2 for its 600,000 iterations of hashing. And it's very, very fast. It uses a hash-based machine access code, I believe it's called. When that comes back, you use the IV, which is another 12-byte from the OS pool. And you run that then through your HKDF, and you get 3 keys. You run it 3 times. The first time each time with a different tag. You get a key for encryption, a key for authorization, and a key for the audit trail. And those are the keys then that you send off for encryption. So it's quite a ways downstream from the original password. And the original password is never stored unless you put it on the keyboard upside down. And you know, it's the secret, and that's the weak point in everything else. So by this time, you have data that's nowhere near what the password is, and your data is pretty encrypted, pretty safe. The hackers really don't go for the data, they go after the password, and it's a science in itself, the way they do it. Most of them are fairly, the hobbyist hacker will not be able to do much at all. It almost takes a nation state with supercomputers to do anything serious, trying to break 256 encryption. So the FIPS requires that the IVs and the salts be generated by the deterministic random bit generators, which is referencing the OS entropy pool. And CBC mode that we have in Xojo is fine for encrypting. It's just not validated by FIPS, so it's not something that we can use in regulated environments. Whereas if we go with the Cipher MBS class and the OpenSSL, then we have at least something that we can call compliant. Just because we use all of these routines and we put something together doesn't mean that you're validated. It just means that you're compliant with what FIPS recommends for encryption in these regulated environments. So the key is not that you want to create your encryption routines and send it off to FIPS, because you'll be spending 7 months and $70,000 getting it validated. But in most situations, your client may not really require validation. They may just require compliant. They might just want to see your routines. It's not an absolute requirement. Generally in the government it is, and depending on how sensitive the data is getting, then you absolutely have to have validated encryption. And there are companies that are validated. OpenSSL has their own version of these routines within. The OpenSSL is a massive system, but within that they have validated routines that are FIPS 3 validated now. FIPS 2 was up to, I think, is being deprecated in October of this year, and then it'll just be the newer FIPS 3. And so we have to get revalidated then. WolfCrypt is another company that produces a very small, tight, validated system that's validated in FIPS 3, and they'll even sell you the package for around $7 grand, and they'll even allow you to brand it with your own name if you want, if you're creating a system that big enough that you can justify $7,000 for just your encryption. So in getting to the point of actually encrypting the data, we need to get a random or randomized IV and salt. We need to run it through many iterations of hashing. We need to make sure that we're using GCM and not CBC or one of the other systems. The GCM authentication tag is handled by the algorithm itself, but I believe you can manipulate that. I think Christian has routines that allow you to even manipulate the authentication tags. And then you need to package it all together properly and send it off for encryption. And you need to know how and where to store the key and to write an audit log of what was being done with the encryption. Now, let's see here. What we're going to show here is, so here's a little app that demonstrates the speed of these things and what happens when we change from Xojo, pure Xojo, to the MBS routines. So if we take load a file, let's just say, here's my little horned owl on 75 megabytes, and we encrypt it with purely Xojo's AES CBC. It encrypts fairly quickly, 400 milliseconds for 75 megabytes. By moving to the AES 256 with the Cipher MBS, it encrypts in 33 milliseconds. So it's a significant difference there. And then if we add in, that's without everything for validation. That's just running the GCM against it. If we throw in the 600,000 iterations and the audit log, then it takes 417. So now the interesting thing here is if we watch it, we'll go to a larger file, like a 500 megabyte file. Takes 2.5 seconds with the straight Xojo routine, and the Cipher MBS runs it at 117 milliseconds. So considerably faster there. And when we do the entire package, it goes to 483. So notice 83 isn't 117, but it's somewhere in that neighborhood, and you still have this underlying 400 milliseconds sitting there. So if we bump this up now to a gigabyte, it takes about 5 seconds, and with the Cyber MBS, 233 milliseconds, quite a bit faster. And if we go to the full package again, we have a 233 and 183 above the 400. What there is a static time frame for the PBK DF2, the 600,000 iterations. So no matter what size file you're encrypting, you're going to be incurring that on this machine, 400 milliseconds of time for it to iterate through 600,000 hashes of that key. Now this also includes writing a log out to a file that has the audit key, and in hospital situations they're going to want an audit log again, like I said, to monitor everything that's done by everybody. And in this case, if you can see that or not, but we have one entry here for what we just did there that has certain information about what happened. It was encrypted, the size of the file, and then the authentication key. And for each time that is done, then this is written into a log into the application support area. And in a medical situation, then they can open this up and they can run it back through the routines, and it will tell you whether this has been tampered with or not. So it's a way of authenticating the audit log. for protecting what's going on in the hospital. And they're very serious about that. The European organizations will charge you up to 4% of your annual income with a violation, depending upon how bad the violation is. And the HIPAA can charge you up to a couple $1 million for violations, depending upon how bad it is. So it's imperative to get this right. You know, make sure your keys are protected, make sure they're truly random. Your IVs are always or never replicated. You never use the same IVs for any of your encryption, keeping away from any pattern making that hackers can see. Now, if you're not in a regulated environment, you can use Argon 2ID for your hashing. It's a little stronger actually than the PBK DF2. It's just that FIPS hasn't caught up to the modern system yet, and it probably won't be until the next iteration of FIPS. So it would be really the way to go in a non-regulated environment. And it's a little stronger for side channel attacks and GPU farm attacks. So it's not so much about what should you use. It's already been decided by these organizations. But how are you going to put it together in order to have the best protection possible, not only for the data and the organization, but for yourself too, because the fees and the penalties can be quite severe. If they rule against you, you can lose your validation, and pretty soon your software then isn't marketable. So here we're talking about for our general context, 2ID, KDF. So we got to think about keys, IVs, your iterations, your random, your OS entropy, where you're getting all of this. So in writing code for your encryption, you have a lot of things to think about. And with my aging brain, that's too much. And so I decided to write a little routine to standardize all of that, so that all you need to do is put together one profile for the type of encryption that you need, and then you just have a simple call, throw out the data and the passphrase, and it hands you back the encryption. And you don't worry about the salts, the IV, all that's done under the hood without dealing it. Right now, the profile is built into the code, and so you can hardwire that in, but I'm coming out with a full, more commercial-like package in about a month now that will handle outside declarations for your profiles. So if you want to do regular encryption, outside of regulated environments, you want to use different types of encryption algorithms, you can. You don't need to do 600,000 iterations. You can cut that down to whatever you'd like, or even cut it out completely. And then it will run through and handle all of that. So in this situation, we call it medical. The context type is medical. You set it there, and away it goes, and it will take care of all that for you. So that is very nice for my brain. All I have to do is one call to encrypt and decrypt. And you can actually get more control if you want by changing the different profiles. But it's easiest for me to make a nice medical or general profile, and then I can run through with just the one call. So it's a module, and it protects you from doing things wrong or forgetting a key, or forgetting how to do a key properly, or reusing an IV, something that we're going to give the hackers a way to get in. So these are all the things we handle. We stay away from strings. It's all memory blocks. We write the audit trail. The audit trail can be expanded to, in a medical context, you would also be logging the patient or the person doing the encryption or touching the data that may be decrypting it and looking at it. So everything is logged along with the authentication key for it. So that's all taken care of inside this module. And I already showed you that. And just a little matrix here as to what is included. You can see in the module on the right-hand side, we do everything there. We don't have to worry about the modes or the iterations or the audit log. And I call it Secure Kit. If you're interested in playing with it, you can go to the website and just download it. You have to use this password. The website's new, and I didn't communicate well with the apparently with the web designer, and he put this password on it that he figured out from the other information I had sent them. So if you use that password on it, I'll try to. It may not ask you for a password by the time you get to it. I'll see if I can get them to change it, because you don't need to do that. But I have a few little demo apps there that show how the HMAC validator works, and it shows how you, well, I can show you right here. So if you have your message up here, or whatever it may be, and you throw in your key, something really cryptic, and it's signed. And so now your message is signed with the authentication key. If we change one little character somewhere, if it's been tampered with either in the message or in the key, then it tells us it's invalid. And I don't know what I took out of there, so it's going to remain invalid. We'll try it again. Or with the taking something out of the key, and it'll tell you it's invalid. Or if we go back, then it's valid. So that just shows how that works for the authentication. For using why memory blocks are so important, you say there can be encoding information within the string system, so you need to keep it clean and stay within your memory blocks for the whole distance. So if we encrypt this, here it is in memory, and if we just set that memory block to nil, we still have the data there. It's still available, so it can be hacked. So it's a simple fix. You just simply wipe it, which we do in the kit, and now it's all zeroed out. So now that is gone. So every time we use a key in any form within the module, as soon as it's done, we wipe the memory so that nothing is hanging around and to be grabbed. And then I had another one. I think that was it. Oh, I've got it. When I was putting this together, I developed a little flashcard demo to help learn all of these terms. And so you can download this also. I've got a little over 100 different cards in here with information on different categories for encrypting in these environments, all the acronyms, which there's a lot of them, and different algorithms, just information all about encryption concerning this, key management, regulations. So you can skip through these, or you can just figure out just certain types that you want to look at, or you can search for things. So you want to see what NIST is all about. And if you want to look at one, you can double click on it. That'll open up a little flashcard type of thing if you want to train your brain and move between the front page and the back page. You know, ask yourself questions and put in your information there. Down here you can modify them or just clear the fields and add a new one in if you want to keep adding more cards for any other topic that you might like. But this just has a lot of information about the encryption system. So if you care to play with that, that's available too on the website for downloading. And I think that's about it. Are there any questions?
I've got a comment. And I understand why doctors like fax machines.
Yeah.
I keep seeing doctors using fax machines. It's like, it's the modern age. Why are they sticking to fax machines? Shouldn't they be doing this? I mean,
Yeah, still works. I'm not sure how they're encoded, you know, when the things are sent. Never even thought about that.
but it seems like fax machines are considered secure, when I can't believe that's really true.
How is it turned into the actual data stream? Is it like the way printers do? Is it some kind of postscript or something?
I think
Sent
it's
it?
a scan. It just scans the data, so it's just an image.
So there'd be nothing to intercept and decrypt. You need to be able to intercept and reassemble
Yeah.
to get the same picture, so to speak.
Yeah.
That, you know, I'm not sure how they classify that in terms of security.
Yeah,
But they do, they still use it, it's widespread.
yeah, very widespread.
Yeah.
It's no problem to hack a line and grab all the data from the fax.
I'm sorry?
For a good hacker, it's not a very big problem to hack a fax transmission. Can be the man in the middle attack.
Yeah, man.
All the thing ever. It's the same as every security from states as the Russians do to intercept telephone as we do with them.
Yeah.
Of course, you can do this with a fax.
Yeah.
If you could get to the fax machine in your office, for example, and insert a piece of hardware in between the phone line and the fax machine.
You won't do this in the office, you can do it in the streets. There's boxes where the cables come
Oh, yeah, you
all
don't have to go in the office, that's true.
Yeah, it's just a stream,
Yeah.
light
And yet,
stream.
and yet that's considered safe. Like, this is way more safe, and you
Yeah.
send files to the internet.
Yeah. Well, like you were saying about the big numbers,
Yeah.
2 to the 256 is
A huge number.
more electrons in the universe.
Right.
It would take centuries to decrypt the data
Right.
itself,
Right.
unless you just happen to hit it right.
Well, the brute force is not really possible, basically,
Yeah.
for all intents and purposes.
Yeah. Yep, any more questions? Yes?
When you have still your job when the quantum day shows up?
I'm sorry, I couldn't hear that.
The quantum day, do you know the quantum day? The quantum day, the day when the quantum computers will
Oh,
silence
They-
all descriptions.
yeah, they're not too worried about quantum computers. They figure by, was it Grover's algorithm that quantum computers will reduce 256 down to 128. Still way outside the ability to
And then you just,
decrypt it quickly.
and then you just use a larger bit.
Yeah.
Like, I mean, 100,
Yeah, go to
well,
512.
124 bits, for example.
Right, yeah. Yeah, so, I don't, everything I've read is that quantum computers will not be a problem with this, but who knows where quantum computers are going to end up,
Yeah.
you know, with what do they call them, the qubits, you know,
Visual brain. Yes, still they're working on cells, computers built by cells, biological cells.
Well, still the best way is just to take the person out to the bar and get them drunk and get their key from them. Then you solve the problem. Okay, thank you.